Hi, my name is Alex Dumitru, and I'm here to tell you about my third year project entitled Hermes, a high-performance software distribution system. My supervisor is Dr. Antonio Pop. So, what is my project about? It's about enabling very fast and efficient updates of software over the cloud. These updates are based on the idea of content-defined chunking, which means that project data is split into chunks of bytes. These bytes live in the cloud, and it's a different approach compared to the historical idea of using binary patches to send updates for software. It's meant to be an open source project, which means it's meant to be picked up by distributors and users who wish to send across software over the network much more efficiently. It comes packaged as terminal commands for both the distributors and the end users, which makes it easy to automate into launcher software and therefore easy to adopt by distributors such as video game distributors. So, what is the exact workflow? There are three main stages. In the top right corner, you see that distributors are responsible for releasing new software versions. They do this by running a script from Hermes, which splits their local data into chunks and then uploads these chunks to the cloud alongside a manifest, which is basically an index of data. The cloud then acts as a simple binary large object storage of those chunks, and those chunks are identified by the unique hashes. And then on the top left corner, end users would update to the latest version through scripts provided by Hermes, and these scripts automatically know to download only new or changed chunks, thereby reutilizing as much as of the local data as possible. So, why is this useful? Historically, the problem of distributing software has been one that has been continuously researched and tried to be made more efficient. Distributors want to send updates very quickly to their users to minimize downtime. The idea is inspired by work done by Riot Games. Riot Games are the team behind League of Legends, and they desire to reduce their end-to-end time from 5 hours to something less, and they've managed to do this by implementing content-defined chunking updates, and they managed to reduce their time to 1 minute, which is a significant improvement. Additionally, distributors want to minimize the storage amount they use for hosting their video game or software data in the cloud, and the amount of energy consumed when sending data to mobile devices, which consume more battery the more data you have to send across the network. This workflow presented here uses data deduplication, which means that it does its best to attempt to have each unique chunk present only once. What that means is that, for instance, if you have the same file content in two files across the same project version, that file content, however large it may be, will only exist in one place. This workflow also minimizes the network bandwidth used for transmitting software by reusing a large amount of local data, thereby also saving energy for software updates on mobile devices. In the demo, I will be showing you a working version with a connection to the Amazon Web Services data store, along with a demo of the benchmarking command used to analyze the speed and efficiency of this tool. The HM script is used to interface with the application through a helpful command line interface, and I have prepared a history of versions for the video game Stun Trolley gathered from GitHub. I'm going to first of all upload this 2.5 version using the screencast demo repo on an Amazon Web Service instance. The upload command reports the new files it will upload and showcases the progress for uploading 11,000 chunks of data. After finishing, the upload command reports it has uploaded around 593 megabytes of data, along with the manifest or index file of the data. Using the AWS Data Store interface, we can search for and inspect the screencast demo folder. The screencast demo folder contains the archived manifest file of our data, along with data chunks identified by their unique hash. If we rerun the upload command, it will complete almost instantly and report 0 bytes uploaded, since Hermes first parses the cloud manifest to compute what new data it needs to transfer, in this case, none. I will now showcase the download command, which I will run with the same cloud connection. We can see two progress bars, one for the new chunks being downloaded and the other for the chunks being reused. The download command reports 593 megabytes downloaded and 0 bytes reused since we started with an empty download location. I will now showcase the partial updating feature. To the same AWS store, I will upload version 2.6 of the data. Updating to the newer version is a much faster operation. As you can see, we are only uploading 2300 chunks. The command reports that we have now uploaded only 140 megabytes, which is the data that's changed between the two versions. I will now run the download command with the same parameters. It will parse the new manifest from the AWS store and download and inject only the new chunks. The download command successfully downloaded only the changed 111.14 megabytes of data. I will finally showcase the benchmark command. Given a folder with sequential versions of the same software, it will upload the first version to the selected repository and then upgrade to each subsequent version, recording performance statistics for each operation. The benchmark command finished, and it saved the benchmark results to a CSV file. This can be easily imported into Google Sheets and analyzed. In this example, we've shown that for the Centrally project, Hermes reuses an average of 73% of data when upgrading between versions. Thank you for watching my screencast. It has been a pleasure developing this project, and I am grateful for the opportunity to showcase it.